Yesterday, for the first time, we distinguished between two different types of collisions. Up until then, it's always been just a collision, right? Two cars hit each other, they stick together, they bounce apart. We haven't paid any attention to a type of collision or distinguishing between one type of collision and another collision. Now we are. The two types of collisions that we have are elastic collisions and inelastic collisions. In both of these collisions, momentum stays the same. Momentum doesn't decrease or increase. In other words, momentum is conserved in both of these collisions. Right? We haven't distinguished until yesterday between these two types of collisions. So if we've used conservation of momentum regardless of what type of collision it was, then it must apply to both types of collisions. Okay? They're indistinguishable from one another in terms of momentum. But there is one thing, one important thing that is different between an elastic and an inelastic collision. What is it? What's that one thing that separates them, Stephen? Good. In an elastic collision, what do you know about kinetic energy, Stephen? What do you know about kinetic energy in an elastic collision? It is or isn't conserved? Right. In an inelastic collision, kinetic energy is not conserved. So if you have a problem in which two cars hit each other or two objects hit each other, you calculate the initial kinetic energy, you calculate the final kinetic energy, and those two numbers are both exactly the same to the right number of significant figures. What would you say about that collision? It's elastic. Good. What would you say about that collision if the two numbers aren't the same? In other words, if you lost kinetic energy in that collision. Kinetic energy is lost. It's got to be good, inelastic. Here's a tough question for you. What would you say if kinetic energy, you did the calculation, you found that kinetic energy was gained in the collision? What would you say? Yes, you would say, I'm wrong. I should do this again. Because kinetic energy won't be gained in the collision. Now, it is possible when you have an explosion to gain kinetic energy, right? Okay. If I throw a rock or a big, heavy medicine ball on ice, and the medicine ball goes one way and I go the other way, momentum stays at zero. But because kinetic energy is a scalar, direction doesn't matter, you do gain kinetic energy. That kinetic energy comes from the chemical potential energy in my body that was converted ultimately to kinetic energy. But that's not a collision. We don't talk about explosions as being elastic or inelastic. We talk only about collisions as being elastic or inelastic. So if you've got a collision and you gain kinetic energy, you're wrong. Do it again. Okay? What's the shortcut? What's the shortcut that sometimes works for us to tell us whether we have an elastic or inelastic collision? Hey, all else fails, calculate kinetic energy. That'll tell you 100%. It's either elastic or inelastic. But there's a shortcut that we can often use to save ourselves the bother of doing that calculation. Jake, what is it? Okay, whether or not the objects bounce apart. What do you know about whether it's elastic or inelastic if they bounce apart? Okay, hold on. No, listen to the question I just asked, right? If two objects bounce apart, what can you tell me about that collision? Good. You don't know whether it's elastic or inelastic if they bounce apart. Elastic, Jake, as you just said a minute ago, they always bounce apart. Okay, they always bounce apart, but sometimes inelastic does too. So if you see two objects bouncing apart, we don't know whether it's elastic or inelastic. If they stick together, what do you know about it? Cassie? You know that it's inelastic. Listen, you can still do the calculation. That's fine. But you can also save yourself the bother of that calculation if they stick together because you know what you're going to get. You know that you're going to have a loss of kinetic energy there. All right? Finally, a couple of last questions here. Give me an example of an inelastic collision. Give me an example of an inelastic collision. Guys, there's only about 1 billion of them. Well, really about an infinite number of them. So I understand if you can't think of one. Dustin? Yeah, car crash. Do they stick together or bounce apart? Okay, stick together. Car crashes stick together. Definitely inelastic. What happens if those cars bounce apart? No, it's almost certainly going to be inelastic as well if they bounce apart because there's deformation there, right? And we said that's the reason why it becomes inelastic is because kinetic energy is lost in the process of converting kinetic to elastic potential energy and back to kinetic again. It will almost certainly be inelastic in that case. Okay. Although if they bounce apart, you're still going to want to do that calculation just to make sure. If they stick together, don't bother. Give an example of an elastic collision, or at least something that's real close to elastic. This one might be a little bit harder to come up with because there's less of them. Yeah. Good. Newton's cradle. Oh, that is a great example. I want you to remember this. That's almost like I planted that answer. I didn't, by the way. Stephen came up with it on his own. I'm not really going to show you this very much because it's not a good example of it. One of the balls doesn't sit properly, so it's not a good example. But this shows you what a Newton's cradle is. You will get a momentum assignment later this year after we've finished our momentum unit. You'll get it while we're doing another unit to provide us with a review of momentum. Question number 1 asks you to explain something about a Newton's cradle, about this. And I'll tell you right now, the answer has to do with what Stephen just said. Okay? He suggested that a Newton's cradle is an elastic collision. The answer has to do with that. Okay, that's not the entire answer, but it has to do with that. And that's where people get hung up on is they don't remember that. Okay? So Newton's cradle is a good example of something that's pretty close to an elastic collision. Can you tell me, Stephen, why it's elastic or pretty close to elastic versus the two cars colliding that were inelastic? Right. These marbles or stainless steel balls or whatever it is that you want to call them, as they hit each other, they deform a little bit, but not very much. So there's not very much of a conversion of energy taking place, therefore not very much kinetic energy lost. The only time we have it truly elastic is when it's subatomic particles. But something like that is pretty close. Okay. All right. We did an example question yesterday, and I think for the most part that it was not too bad. I'm going to leave you right now for the next 10 minutes in class here to work on these 2 questions on page 482. I'll remind you of a couple of quick little things. Number 1, we calculate EKI separately from EKF. Do not do this. I see people doing this all the time. They set EKI equal to EKF. Why do I not want to do that? What's wrong with that? What's wrong with saying EKI? Oh, okay, it's 1/2 M1 V1I squared plus 1/2 M2 V2I squared equals so on and so on and so on. What's wrong with doing that? The question is determine if it's elastic. If I do that, what am I telling you before I even do anything? That it's elastic. Okay? We don't know if they're equal. Don't set them equal to each other. We don't know if they're equal. It's not like conservation of momentum where we know the momentums are going to be the same. We don't know that here. Calculate EKI, calculate EKF, round them to the right number of significant figures, and then compare them. Now, the second thing that I wanted to remind you of, if you've got something to the south, something to the west, something to the left, something down, what do you do with that direction when calculating kinetic energy? 2 words. They both start with I. Good. Ignore it. We don't pay any attention to direction when using kinetic energy. Now, if you have to do conservation of momentum somewhere, pay attention to direction. But for kinetic energy, ignore it. Got it? All right, see what you can do with those 2 questions, please.